What's up, everyone? My name is Vincent, and today I want to show you how to use the integral test. So for these three questions here, we want to use the integral test to determine if the series converges, diverges, or just state that the test doesn't apply. Now, here is the integral test, just in case you don't have it in your notes. So if you need this, here it is, and you could write this in your notes. But just know that the only time you're allowed to use the integral test is when you have a function f of x that's continuous, positive, and decreasing for values of x greater than or equal to 1, which really just means like x greater than or equal to 1 just lines up with the series, that the series is starting at k equals 1. And the way that we apply this test is that we're going to set up a function f of x, which is essentially the same thing as this expression a of k here, except we're replacing it with x. And if this improper integral converges, that means that the series converges. But if this improper integral diverges, that tells you that the series diverges. And remember, if any one of these three conditions in the beginning is not met, that means the test doesn't apply. And the last thing to mention here is that just be careful. The value of the integral, in the event that it does converge, is not equal to the value of the series. Okay, so we're going to get started with question 1 here. We're going to apply the integral test to see if this series converges or diverges. So what we'll do first is we're going to just define f of x to equal 1 over the cube root of x plus 10. And if we want to rewrite this a little bit nicer, this is x plus 10 to the negative 1/3 power. This is going to help us in a moment when we have to take the derivative. But for the first step, when you want to establish that f of x is positive and continuous, we don't have to write the most rigorous explanation. Like just looking at this, when x is greater than or equal to 1, 1 plus 10 or 2 plus 10, anything bigger than 1 is going to result in a positive. The cube root of a positive is positive, and 1 divided by a positive number is positive. So that condition is satisfied. And the cube root function here is continuous as long as x is not equal to negative 10. But for values of x greater than or equal to 1, there's no restrictions on which x values we could plug in here. So we could say first that f of x is continuous and positive for x greater than or equal to 1. So then the next thing we need to show here is that this function is decreasing. And the way we do that is we're going to apply the first derivative test. So the first derivative here, and notice I already wrote it in the form here of this power, is I would use the power rule. I would have negative 1/3 times the base x plus 10. And now we're subtracting 1. So negative 1/3 minus 1 is going to give us negative 4/3. And I should use the chain rule here, but the derivative of x plus 10 is just 1. So I could write the times 1 out here, but it's not that important. So I will rewrite this to make it look a little bit cleaner. This is negative 1 over 3 times, and x plus 10 to the negative 4/3 is the same thing as the cube root of x plus 10. And this expression here is raised to the 4th power. Okay, so this is just an alternate way of writing out this expression here. Now this is negative 1 over 3 times the cube root of x plus 10 to the 4th power. But now just looking at this, we could see here by analysis that this expression, I have x plus 10 to the 4th power. And like we said before, this function was continuous and positive for x greater than or equal to 1. The domain of this function, the domain of the original function, is simply just x does not equal negative 10. So if I look at the first derivative and we make a sign chart, and we just cut out negative 10 here, okay, negative 10 is not allowed in the domain. Well, all I really need to check here is what's going on to the right of negative 10. And when we evaluate this here, just by analysis, we could see that no matter what value of x I plug in except negative 10, when I raise it to the 4th power, that's going to be positive. So this part here is going to be positive no matter what I plug in, as long as I don't plug in x equals negative 10. So I have something positive here times a positive 3, but I have a negative 1 in my numerator, which means the entire thing here is going to be negative no matter what value of x I plug in to the right of negative 10. This is also true to the left of negative 10. If I were to plug in negative 20 and raise it to the fourth, I have a positive denominator under a negative numerator. So what this sign chart tells us is that f of x is decreasing for all x values greater than or equal to 1. This is one of the steps we need to establish. Okay, so now after we have this established here, this allows us to apply the integral test. The three conditions have been met. All right, so now we're going to set up the improper integral. So we have the integral from 1 to infinity, and we're going to write in f of x. And f of x was equal to x plus 10 to the negative 1/3 power. But then what we want to do so that we could evaluate this, we're going to have to set up a limit. The limit as, and we could choose a different letter, let's say t. The limit as t goes to infinity of the integral from 1 to t. So now this is essentially matching this integral that we have here. And we write our function. We have x plus 10 to the negative 1/3 power. And all we need to do here is evaluate this integral. So I could do a u substitution here, but if I let u equal x plus 10, the derivative of x plus 10 is 1. So this is a situation where I could just use the power rule for antiderivatives, and it's not going to matter. Later on, we'll have to do a legitimate u substitution, but here I could just evaluate this integral straightforward. So this would be the limit as t goes to infinity. And when we do this antiderivative, we're going to have x plus 10 in parentheses. And when I do negative 1/3 plus 1, I'm going to have a power here of 2/3. And then I write the reciprocal here in front, 3/2. And then I write my limits of integration from 1 to t. So then we just have to evaluate this. This is now the limit as t goes to infinity. And we just make our substitution. We have 3/2. And the 3/2 we could drag out in front here. We'll just write that outside the limit. So we have 3/2, and we've got t plus 10. See how we're just plugging in the upper limit. So we have t plus 10 to the 2/3 minus, and now we have to plug in the lower limit. 1 plus 10 is 11 to the 2/3. So then the last thing we need to do here is evaluate this limit. And notice as t goes to infinity, we would have infinity plus 10 to the 2/3 power. This expression here is going to go off to infinity. So when we subtract this small constant here, it's not going to matter. The entire limit is going off to infinity. And multiplying by a constant out in front doesn't matter either. This whole thing is going to go to infinity. So what this tells us, since this limit goes to infinity, by the integral test, this tells us that the original series diverges because this improper integral diverges. Okay, for the second question, it's the same idea. We need to show that f of x is positive and continuous for x greater than or equal to 1. Well, first let's establish that f of x, in this case, is going to be equal to x e to the negative 2x squared. So once we get here, this we could just do by analysis, that e to any power is positive. And if x is greater than or equal to 1, the expression x is positive. So we have a positive times a positive, which would be positive. And also, we know that negative 2x squared is a continuous function. E to the x is a continuous function. So the composition of two continuous functions is continuous. x is continuous, so the product of two continuous functions is continuous. So that's enough for us to say what we need to establish for step 1. Okay, for the second step, we have to find the first derivative to show that f of x is decreasing. So we'll do that now, and we have to do the product rule with the chain rule. So for f prime of x, we have let x represent the first part of the function here, and then this represents the second part of the function. So the derivative of x is 1. So we have 1 times e to the negative 2x squared plus x, and this is where we have to be careful. The derivative of e to the negative 2x squared is e to the negative 2x squared times the derivative of the exponent, which is negative 4x. So if we clean this expression up a little bit, the derivative is e to the negative 2x squared, and we would have minus 4x squared when we multiply negative 4x times this coefficient x. We'd have minus 4x squared e to the negative 2x squared. But in order to determine if this function is decreasing, we should factor the derivative. So we'd have f prime of x is equal to e to the negative 2x squared. Let's make that neater. And we'd have times 1 minus 4x squared. So now to apply the first derivative test, f prime of x equals 0 when, and if we look here, notice this first part that we factored out is always positive. So we're not going to get a 0 out of this factor. The only time we're going to get a 0 is out of this. So it's when 1 minus 4x squared is equal to 0. Now there's a few ways we could solve this, but I could just rearrange this to say that x squared is equal to a fourth. And if x squared is equal to a fourth, this tells us that this is true when x equals plus or minus a half. So now we'll make a sign chart for our first derivative. So we're looking at f prime of x here. The only roots we have for the first derivative are at negative 1/2 and positive 1/2. Now the shortcut to assigning this positives or negatives here is I just analyze 1 minus 4x squared. And what I imagine here is the roots are at negative 1/2 and positive 1/2. And since it's a negative 4x squared, a negative in front of the x squared tells us it's going to be a parabola opening downwards. So when I need to assign the signs here, this thing starts off negative, then it goes positive between the roots, and then it goes negative again. So this is just a quick way instead of plugging in test values. So now making use of this, what this allows us to say is we really just care about when x is greater than or equal to 1. And notice our first derivative is negative on that interval, which tells us f of x is decreasing for values of x greater than or equal to 1. So what this tells us is that the integral test does apply here. So we'll apply the integral test now. All right, so now we could apply the integral test. So let's set up the integral from 1 to infinity of f of x. And remember, f of x was x e to the negative 2x squared, and then dx here. So this is a situation where we have to do a u substitution. But first, we're just going to rewrite this as the limit as t goes to infinity, the integral from 1 to t of f of x. And once again, that's x e to the negative 2x squared. So for this one, what we'll do is we'll just go on the side here and evaluate the integral first. So if I had the integral x e to the negative 2x squared dx, you might be able to just do this in your head, but I'll just show the steps. We would have u equals negative 2x squared, and then du is equal to negative 4x dx. So then if I solve for dx, that would give me du over negative 4x is equal to dx. So then here we make the substitution. We would have x times e to the u power, where u is negative 2x squared. Dx is du divided by negative 4x. So then the x's cancel out here. So the integral is now just negative 1 over 4 e to the u du. And in this case, the integral will be negative 1 over 4 e to the negative 2x squared. And I would have to tack on a plus c if I'm just showing this work on the side for an indefinite integral. But this is a definite integral. So when we transfer that idea over here, I'm not going to need that plus c. So this is the limit as t goes to infinity. And the integral is negative 1/4 e to the negative 2. Let's make that a little neater. Negative 2x squared. And the limits are going from 1 to t. Okay, so moving on with this. This is the limit as t goes to infinity. And we've got negative 1/4 is our constant. And this is e to the negative 2 t squared minus e to the negative second power when we substitute in 1. Okay, so all we did was just plug in the limits of integration here. But then the only term we have to be really careful with here is the first one. So let's take a look. This is the limit as t goes to infinity. And once again, this is negative 1/4. And I'll rewrite this as 1 over e to the, and let's just fix that, maybe make more space. 1 over e to the 2t squared. So I'm just writing this as a positive exponent. So I'm writing it 1 over e to the 2t squared. And this is minus e to the negative 2. So then what we have to just be mindful of here is as t goes to infinity, this first part, 1 over e to the 2t squared, goes to 0 because I have essentially 1 over infinity. So this first term is going to cancel. So the only thing left here in our limit is minus e to the negative 2, and I'm multiplying by this negative 1/4. So this is going to result in 1/4 times e to the negative second power. So what this tells us is that the improper integral converges. So since the improper integral converges by the integral test, that means the series converges as well. Okay, so now let's take a look at this last question here. If we let f of x equal x over square root x squared plus 4. So we've defined f of x. This function is positive and continuous when x is greater than or equal to 1, because if I plug in numbers bigger than 1, in the denominator here, I have the square root of something that's always positive. And if I have a numerator that's greater than or equal to 1, then f of x is positive for those values. And here, this is a function that is actually continuous for all values of x, because there are no restrictions here on what I could plug into the square root, since x squared plus 4 is always positive. So I could make the first statement here that f of x is positive and continuous for x greater than or equal to 1. So then the next thing we would need to do here is look at the first derivative and show that f of x is decreasing for x greater than or equal to 1. So what I'll do first is I'm going to rewrite this as x over, and I'm going to write this in parentheses, x squared plus 4 to the 1/2 power. Okay, so that's going to allow us to do quotient rule. So when we take the derivative here, we've got f prime of x equals, and now let's go ahead and use the quotient rule. So we've got x squared plus 4 to the 1/2 power times the derivative of the numerator. So we've got, that's the first part here, and then minus x times the derivative of the denominator, and this part's a little bit trickier. So we've got power rule first on the outside function, So 1/2 x squared plus 4 to the negative 1/2 power. And then we're going to multiply by the derivative of the inside, which is 2x. And we're dividing by the denominator squared. And in this case, if I do square root of x squared plus 4 squared, the radical simply disappears. So the denominator is just x squared plus 4. And let's just simplify the numerator a little bit. So what we'll do is, I'm going to put this back in radical form. We have square root of x squared plus 4 first, minus, and now 1/2 times 2 cancels out, and we have x times x is x squared. And then x squared plus 4 to the negative 1/2, I could send down to this denominator. And by denominator, I mean if I turn the second part here, this part of the expression here, into a fraction, I would have x squared over radical x squared plus 4. And this is all over x squared plus 4. Okay, so then this is where the analysis is going to start to come in. If I want to know the sign of f prime of x, what I need to do is look for potential roots and determine if the first derivative is positive or negative. So one thing to be mindful of here is that the denominator is always positive. So really what we need to look at here, if there are going to be any x values that make the derivative negative, it's going to come from the expression in the numerator. So what we should do is look for when f prime of x is equal to 0. So f prime of x is equal to 0 when the numerator is equal to 0 and the denominator is non-zero, which is not going to be a problem because the denominator is always positive. So if we set the numerator equal to 0, now we could rearrange this. Another thing we could do from here now is cross multiply, giving us the expression x squared, or equation x squared equals x squared plus 4. But here's our problem. If we subtract x squared on both sides, we get the absurd statement 0 equals 4, which is a contradiction. This is the symbol for contradiction. So what this tells us is that f prime of x could never equal 0. So f prime of x has no roots. So then what we would do here is determine the sign here. So what is the sign of f prime of x? Well, if we borrow the derivative from before and we look at the sign chart, all we would have to determine here is a single value. So let's say we were to plug in 0 to our first derivative. Well, what we would have is, we would have the square root of 0 plus 4, which is 2, minus 0 divided by the square root of 4, which is 0, divided by 0 plus 4, which is 4, which is equal to a half, which tells us that if we had to make a sign chart for f prime, we only need to pick a single test value, and that test value yielded something positive. So there we have it. If the first derivative is always positive, that means f of x is always increasing. And if f of x is always increasing, that means we cannot apply the integral test, because for the integral test, we need f of x to be decreasing for values of x greater than or equal to 1. So let's write our conclusion. Okay, well, this is going to conclude this video on using the integral test to determine if a series converges or diverges. If you found this video to be helpful, please click the like and subscribe buttons below. It really helps me grow this channel. And if you got any requests, topics that you want me to cover, leave them in the comments section below. And thank you for watching.